nice short video, at least this part of it. I'll add on the video regarding the drawing of the nephron, showing the capillaries where filtration, reabsorption, secretion occurs, where what the major substances are, and so forth. And again, of course, you're taking an online exam. You can't draw on the computer screen, much as I'd like for you to be able to, but you can't do that. So obviously, the capability to visualize this drawing is going to be important regarding any short answer that I might ask you. As with the previous major question about metabolic pathway through the mitochondria and glucose metabolism, it may be that I post a picture and have you fill out the steps along the way, fill out the little molecules that would be important along the way. So it could be a leading thing like that, or it could be I ask you to do things in steps, or I'll have to break it down. I'll have to figure out exactly how to ask this question. But being familiar with that picture and that little video we went through will help you tremendously, no matter how I ask the question. So let's look now at the nephron, and we're going to begin with the blood vessels that are going into the nephron. And of course, we're starting with the larger diameter afferent arteriole here. As it goes into Bowman's capsule, coming out of it will be the thinner diameter efferent arteriole. And Bowman's capsule we'll go ahead and do in black. What the heck? And let's go ahead and draw it around. There's Bowman's capsule. And then inside Bowman's capsule, of course, a capillary bed. And you'll have to, I'll just join these lines together, forming this dense capillary bed, and then coming back out eventually to form the efferent arteriole. So here we have the glomerular capillaries, or the glomerulus. Do your best to spell this. I don't know, have any clue how I'm going to ask this on the online exam, but I'll figure out a way, don't worry. So certainly aspects of this picture will be evident. This is the afferent arteriole right here. Oops. And then the other one is the efferent leaving the renal corpuscle. And so from this point in the back of the renal corpuscle, let's make a little break right there, we'll have the first segments of the and they'll be quite windy and twisty, and this is the proximal convoluted tubule. Okay, so labeling this part, this is the proximal convoluted tubule. Remember, we can abbreviate as the PCT. Eventually, we're going to progress to an area where we're going to see this hairpin loop. We'll come back up, and then we'll see it over on this side, beginning to form the distal convoluted tubule over here. This is the nephron loop, or the loop of Henle. And so this is the nephron loop. I would suggest when you learn this that you study it in terms of layers. So start out by doing the actual components of the nephron, and then begin looking at the cardiovascular components, and then begin looking at the processes that are going on. That's all that I expect you to know. And so that's what I'm doing right here. I'm just simply drawing them, and I'd like to show you while I'm drawing them so that you maybe perhaps get a better sense of what's going on. These are several distal convoluted tubules that are entering the collecting duct. And the collecting duct is permeable to ADH, don't forget. Now over here, let's go back and label this guy. This is right here. This is Bowman's capsule, or you may also call it the glomerular capsule. Bowman's with an apostrophe. Okay, so now we've got all of our various components labeled. Let's go ahead and add in the bloodstream now, and do that in red/pink. And so what we're going to see is this afferent arteriole is going to have a lot lower blood pressure, and we're going to see it eventually form into these capillaries that are going to surround the proximal tubule as well as the distal tubule. Then they will leave the distal tubule, and we'll see them go to the loop of Henle eventually. Okay, and they'll surround the loop of Henle, but these are no longer those types of capillaries. They're called the vasa recta. Okay, so the vasa recta are the capillaries that surround the nephron loop. Up here in the tubules, they're called the peritubular. The name actually makes sense. They surround the tubules, peritubular capillaries. Okay. So there's our blood vessel system. So now we've got 2 layers done, and now we're ready to start talking about the processes, and the processes are going to be delineated. So over here, we know we always have filtration because of blood pressure issues. We always have an outward push, formation of the filtrate that's eventually going to enter the proximal convoluted tubule. So process 1 is filtration and happens in Bowman's capsule. Process 2 here is going to be reabsorption. And reabsorption is going to involve moving stuff out of the tubules and into the bloodstream, and is going to involve primarily sodium. Remember, that's what we're most concerned with, and water. So sodium and water are the 2 major components getting reabsorbed here. So the second major process that is occurring here is reabsorption. This happens not only in the proximal tubule, but also in the distal tubule to some extent as well. And we'll see sodium and water getting reabsorbed here. Now we also have reabsorption in the nephron loop, but it's a little more limited. In the descending limb of the nephron loop, we have only water that is allowed to exit from those cells. In the ascending limb of the nephron loop, we have only sodium ions that are allowed to exit. And this way we're adjusting the concentration found in urine in the descending versus the ascending limb. Now the third major process that's going to occur is secretion. And secretion, let's make it orange. Secretion is going to involve the removal of compounds from the blood that were not initially filtered out. It's going to be a major process, mainly in the distal convoluted tubule. So we're going to take stuff out of the bloodstream and push it into the urine. Okay, and the major things are hydrogen ions and drug metabolites. A little bit goes on here in the proximal, oops, the wrong way there. In the proximal convoluted tubule, we'll also see stuff exiting out of the bloodstream and going into the urine here. So that's secretion. Primarily, we're worried about the hydrogen ions there. Now, you're almost done. Not too horrible a drawing, not like that metabolism one at least. And on this side, we're going to be looking at the actions of ADH. And ADH is going to allow for openings to occur. These are water channels. All right, so each one of these is a water channel. And when ADH acts on a water channel, it will open it. So we'll go up here to our little eraser. Open that little sucker up. Doesn't want to. Okay, we'll open that. And we'll see that these water channels are now open and H2O can flow out. Depending on how much ADH is there, will depend on how much water exits from the urine here. It depends on whether you're super hydrated or very dehydrated as to how much ADH will be present. Let's look at the rules that govern that. And so typically we associate this with blood pressure. So as blood pressure is increasing, right, then what we're going to expect is we need to get rid of some water. And so what we would expect then is that ADH will begin to decrease as blood pressure is increasing. And that will mean that our urine volume will be higher. Again, this is one of those generally true things as long as you're healthy, and our urine concentration will decrease. On the other hand, as blood pressure is decreasing in the body, this is a dehydrated state. You're going to want to retain all the water you possibly can, so your ADH levels are going to go sky high. Your urine volume should decrease and become very thick and syrupy, and your urine concentration gets very elevated. So these are the general rules governing ADH release and the establishment of a hypertonic or hypotonic urine. The last thing we're going to talk about then is the process of concentration of the urine. Let's see which one I want to pick. I haven't used that, although it doesn't look significantly different. Urines that's forming here in the proximal convoluted tubule is about 300 milliosmoles per liter. That's about the same as plasma, so we'll just say it's 1x concentration. Then as we go through the descending limb of the loop of Henle, or the nephron loop, we know that only water's being removed, so we're concentrating, right? And by the time we get down here, we're about 4 times as concentrated as we were up in the proximal convoluted tubule. Then as we move back up and we're only removing sodium, we're going to get much, much less concentrated. And in the entrance to the distal convoluted tubule, we're only about 1/3 as concentrated. By the time we go through these processes and re-enter the collecting duct, we start out at about, again, 1x. In a typical urine formation, you want to end up with about 4 times the concentration of plasma as you empty into the papillary ducts. That's it. Know it. You're going to see something about this on the exam. Good luck. Take care. ADH is obviously very important. It's associated with blood pressure. As blood pressure is going up, you would expect us to want to retain less water. So as blood pressure goes up, ADH values in the bloodstream should go down, leading to more water retention, thus an increased volume of urine and a decreased concentration of the solutes in urine. On the other hand, as blood pressure is going down, which the body is much more concerned about, ADH levels will rise, causing a greater reabsorption of water, and so that water will enter, helping with blood pressure, but the water's coming out of the urine, so the urine's going to be more concentrated, and it will have a greater, so it's more concentrated, but the volume will be less. On this last little part about the renin-angiotensin-aldosterone system, just realize that when blood pressure drops, there are mechanisms at the afferent arteriole primarily. This mechanism is the juxtaglomerular apparatus, and these juxtaglomerular cells have the capacity to sense through fairly complex interactions that I'm not particularly going to test you about, to sense when there is a drop in blood pressure. And when there is, then they will secrete a compound called renin that activates angiotensinogen in the blood. It's an inactive compound, and it will activate it to angiotensin 1, AT1, and then through the actions of angiotensin converting enzymes, or ACE, you will create a much more powerful activator called angiotensin 2. Angiotensin 2 by itself is a very potent vasoconstrictor, which will increase blood pressure. It will also cause aldosterone release, which promotes sodium retention in the blood, hence water follows, and that will also lead to jacked up blood pressure.